Hey guys, I hope that you guys are behaving yourselves and excited to learn new things, even when I'm not here. I'm probably having a great time at Disney, but anyway, I'm making a video for you, so you're welcome. YouTube famous. All right, so here's what we've talked about the last couple of days. We've added functions, we've subtracted functions, we've multiplied functions. Well, now we're going to talk about dividing functions. Well, it has its own special name. They're called rational functions. And the most basic form is h of x or f of x or g of x, whatever, equals 1 divided by x. So here is a picture of a graph of that. So it's just pretty simple, but there is a break in the graph, and we're going to talk about why there's a break in the graph. There's also another break in the graph here, and we'll talk about that too. But this is the parent function. We've talked about parent functions before. This is the parent function for rationals. So going back, so we have rational functions here. H of x equals 1 over x. That's the equation of the graph that we just saw. And so if you think about why there might be a break in the graph at 0, if this is the equation here, why might there be a break in the graph at 0? And if you think back to what we've talked about in the past, the denominator can't equal 0. Okay, it's not legal. We can't do it. So we can't have anything where x is equal to 0. So what that means at 0 is that it's undefined. Okay, and what that turns into when we graph it is called an asymptote. We talked about asymptotes a little bit when we talked about cosecant, secant, tangent, and cotangent. So this is coming back up. When there's a 0 in the denominator, it doesn't work. We can't use it. So there's going to be a big break in your graph called an asymptote. So we're going to talk about asymptotes a little bit in a minute. But first, let's kind of break down each one of these things. So first we're going to talk about x-intercepts. So where might the graph intersect the x-axis? Well, it's when the numerator is equal to 0. That's going to be an x-intercept. And we talked about this a little bit when we talked about polynomials. So we had like x squared minus 2x minus 3 or whatever, and then we set this equal to 0 and use the quadratic formula. I just wrote that down, so I don't know what it would be. But if we broke it down something else into minus 1, there would be an x-intercept here if we set it equal to 0, and there would be an x-intercept here when we set it equal to 0. So that was when we were graphing polynomials last week. So that's an x-intercept whenever the numerator is equal to 0. The denominator, whenever it is 0, it's causing your graph to be undefined. So here, when this equals 0, that doesn't happen. I got interrupted, sorry. So I think what I was saying before, so when 1 equals 0, that can't happen. So there's no x-intercepts for this one. And part of that, when this one equals 0, there is an asymptote at 0. So this can't happen. So there's no x-intercepts, and this has an asymptote at x equals 0, which we saw here. There's an asymptote here. It's breaking your graph. And so what that would look like would be x equals 0. There'd be a dotted line there, kind of breaking up your graph. All right. Okay, so that's kind of x-intercepts overview. Then we have two different types of undefined locations. So one of them is a vertical asymptote, what we just saw on the graph. The other is called a removable discontinuity or a hole. We talked about discontinuous, so that it just means that it's not it's not continuous. It doesn't connect. So a removable discontinuity means I just plucked one little thing out of the graph, and so it's removable. That's called a hole. So vertical asymptotes versus removable discontinuities. So here I have an example of an equation, and we have factors here. So I have x minus 3 and x plus 2 in the numerator. I have x plus 2 and x minus 7 in the denominator. So one of these is going to divide out, and the other one is going to be x minus 7 in the denominator. So x minus 7 equals 0. I'm going to set each of the terms, or each of the factors, equal to 0. So I'm going to have a vertical asymptote at x equals 7 when I solve. I'm going to have a removable discontinuity because this one divided out, so this one divides out, and this one is when the denominator equals 0. So this would be x plus 2 equals 0, and so that would be x equals negative 2. So there'd be a hole in my graph, a removable discontinuity at x equals negative 2, and there'd be a vertical asymptote, a line, breaking it up at 7. So this one would look like just an open circle. There's a hole in my graph, and this one is a big blocked line. Going back to the last question that we had, x minus 3, this would be my x-intercept at x equals 3. Okay, so that's kind of how that breaks down. Anything that divides out is my removable discontinuity. Vertical asymptotes are anything that's left in the denominator when that equals 0. All right. Okay. Then we have horizontal asymptotes. Okay. Horizontal asymptotes or slant asymptotes. And then this is when this happens. So if we have a problem where the degree is the same. So on that last problem that we had, f of x equals x squared over x squared, and I'll give myself some coefficients here. So the coefficient is just the number that's in front of x squared. And so the horizontal asymptote, horizontal is this direction, so it'd be a horizontal break in the graph, and that would be at y equals 3/4, because this is the coefficient, and the degree, we talked about degree when we talked about polynomials, when the degree is the same. I lost my train of thought. So we have the coefficients because the degree, the highest exponent, is the same. So 3/4 is going to be my horizontal asymptote. So y equals 3/4. This would be like, if this were at 1, this would be 3/4. If the degree is small over large, so the degree is smaller, so this would be like x over x squared. So the degree is smaller because this is a 1 over 2. The horizontal asymptote would be at y equals 0. So it would be right here on your x-axis. That would be your horizontal asymptote. Your slant asymptote, we're not going to talk about a ton. It's when it's large over small, so it would be x squared over x would be that kind of situation, and you'd actually have to divide to figure out what that equation is. So we'll talk more about that later, but kind of I want you to know that it's going to be a slant asymptote. So that's kind of horizontal. And let's see. Okay, so let's kind of walk through all of this together. So this one, the degree on top is smaller than the degree on the bottom. It'd be a 1 over a 2. So it's small over large. Okay, small over large, that means my horizontal asymptote is at y equals 0. My x-intercept is when the numerator equals 0. So when x equals 0, x is going to equal 0. So there would be an x-intercept at the origin. Nothing divides out, so there's no removable discontinuity. The vertical asymptotes, so ones that are up and down, would be where x minus 1 equals 0 and where x plus 2 equals 0. So I have x equals 1 and I have x equals negative 2. So there's going to be an asymptote at 1 and at negative 2. All right, so that's kind of the big picture that we have here. So this is a little bit more concise for you to look at here. X-intercept is when the numerator is 0. Oh, I forgot to talk about this. Y-intercept is when you divide the y-intercept for the numerator and the denominator. So on this last one, this one doesn't have a y-intercept. It's where, I guess it's where x equals 0. So your y-intercept would be 0 something. So when x is equal to 0, we plug in 0 here. 0 minus 1, 0 plus 2. So this would be negative 1 times 2, but that doesn't really matter because it's 0 divided by all of that. So it would be 0, which, duh, that makes sense. So your x-intercept and your y-intercept are the same location at the origin. So that's kind of basic, real quick, through all the pieces of your rational function. Okay, I'm going to make another video, and we're going to talk about kind of more specifics of like what that looks like.